So March the 3rd, 2021, this is lecture 11 in 569 Emergent States of Matter. And we are talking about quasi-particles. So what we discussed last time was the idea that we can write down the energy of a many-body system in the following way. We'd break it down into a complicated many-body ground state that we can't calculate anything about because there's too many strong interactions. And then once you are exciting the system above that ground state, at least only weakly, typically by thermal fluctuations, then what one tries to do is write down the energy in the form of a number of states in terms of the single particle quantum states, i.e. the momentum, P, and an energy associated with that. And then beyond that, you would have interactions between the quasi-particles. So we're talking about what's going on over here. And so the idea of a quasi-particle is that I can somehow write down the energy in this way, where this thing here is the quasi-particle spectrum or dispersion relation. And it's a many-body property of the system. So it's not really true that the system is made up of non-interacting particles. But if I write the system like this, and if the interactions are weak, then to a good approximation, I can think of it in that way. And so this is a very helpful way to try to decompose the energetics of a many-body system into a ground state where it's horribly complicated, and then a few weakly interacting excitations above that, which can be thermally excited. And so the application of that to superfluid helium, that idea was made by Landau in the 1940s, and he guessed the form of epsilon of P or epsilon of K, the dispersion relation, in the way shown over here on the left. And we saw that it had a part where the energy grew linearly with wave number, went to zero at long wavelengths, and then there was this Rotel minimum, and then finally you got into a range where in fact you would not have non-interacting quasi-particles at all. And so what we ended last lecture doing was trying to ask what the thermodynamics were, and what we're doing is essentially what Landau did backwards. Landau basically said, let me assume, what do I need to assume for epsilon of P in order that the heat capacity data can be understood. And so what I want to do now is I want to just finish the calculation of the heat capacity. So the way we write down the thermodynamics, these things are quasi-particles, so they are not conserved, unlike real atoms. So their chemical potential is zero, even though the chemical potential of the actual atoms is -7, and it's minus 7K. Why minus? Well, because they're bosonic systems, and bosons always have a negative chemical potential. And the thermodynamics then is just given by the Gibbs distribution, and from the Gibbs distribution we can work out the occupation number of any given single particle quantum state K, work out the partition function, and so we can write down these general formulae as shown in the left panel. So what we ended up doing at the end of the lecture was we computed the free energy of the system at low enough temperatures that we don't need to assume anything other than the fact that the quasi-particles are the phonon degrees of freedom, which have a linear dispersion relation. So we simply then have to plug that value of epsilon of K into our general formula for the partition function of the system. And this integral turns out to be one that it's quite straightforward to do. And so the answer is shown over here. So what this tells you then is that the phonon free energy, which is the difference between the total free energy and the ground state energy, which we can't calculate, is something that goes as kt to the fourth, which you may find reminiscent, very much reminiscent, of the Stefan-Boltzmann law in blackbody radiation. Okay, so that's the free energy. So I want to start today's lecture by then computing the entropy. So the corresponding entropy of the phonon degrees of freedom is just given by minus d by dt of the phonon free energy. And then you just simply have to differentiate. And so what you get is for pi squared v kb kbt cubed over 90 h bar c1 cubed, like so. And the total energy of the phonons, the internal energy, is given by the Helmholtz free energy plus T times the entropy. And so when you work that out, you just get pi squared V over 30 h bar C1 cubed times KT to the fourth. And then if I want to work out the heat capacity at constant volume, so that is, I'll write it like this. And this is just T ds phonon by dt. And what you get is kb times 2 pi squared v kbt cubed over 15 h bar c1 cubed. So some of these numbers you may recognize, they're all exactly the same, come from the same reasoning as you do in as you get them in black body radiation. And so this is a very nice result, because what it tells you is that by measuring the heat capacity, which is something easy to measure, relatively speaking, then what I can deduce is I can see that it goes as T cubed. And so that tells me that there has to be a phonon branch of the spectrum, and that was Landau's original argument. And then the other thing I can do here, everything else here is fundamental constants, except for this thing, which is the speed of first sound. And so by measuring the heat capacity at low temperatures, whoops. We can measure the phonon sound speed. So that's at the lowest temperatures, below about 1 degree. So now we can ask, well, what happens at higher temperatures? So I'm just going to simply write down the results for you. So now you have to worry about the rotons. So in this range, the roton gap, that was about 8 Kelvin. So delta is still much greater than KUBT, but it's not negligible. And so if I put that formula, this formula for the energy spectrum into my formula for the free energy, then what I'm going to get is I'll have a logarithm of 1 minus e to the energy spectrum. So this is minus beta delta plus h bar squared over twice the effective mass times k minus k naught squared. And then I can just simply expand the logarithm because of the delta being much larger than kt. And so this then can be approximated as e to the minus beta times delta plus h bar squared k minus k naught squared over 2m star. And so that means that I can essentially replace this factor over here this factor which comes from the Bose-Einstein distribution, I can simply replace that with the classical Boltzmann distribution, and so I can work out the free energy for protons. So the formula is in the notes. Let me just write down the final result. What you get is minus V times kBt to the 3/2 e to the minus delta over kBt times a factor 2, whoops, not no pi, so used to writing pi every time I write down 2. Occupational hazard, I suppose. 2 k0 squared m star to the 1/2 over 2 pi cubed to the 3/2 Planck's constant. So this is for what it's worth. This is the contribution that the protons make to the free energy. You can see that there's an exponential dependence due to the activation of the proton gap, and then there's a power law prefactor which gives us t to the 3/2. Okay, so then you can go ahead and work out the heat capacity and the entropy and the heat capacity. So when you go ahead and do that, what you find is that the heat capacity for the proton part of the spectrum looks like the number of protons, which I'll define in just a minute, times 3/4 plus delta over kBt plus delta squared over kBt squared. And n proton is minus the free energy divided by kBt. So that there's a complete description of the thermodynamics. So you can measure the heat capacity, and so if you try to ask yourself, what do I need to do to work backwards, then you get Landau's excitation spectrum. Okay, so that's pretty simple. So now let's move on to something more interesting, which is Landau's theory of superconductivity, of superfluidity.
Can I ask a question?
If it's quick.
Yeah, so why can we separate the contribution from proton and phonon? Shouldn't we just plug in the complicated dispersion into the dispersion?
Yes. If you wanted to get it really accurately, that's what you would do. But in the different temperature ranges, these are the different contributions that you get. So this is just trying to simplify.
Okay, I see. Thank you.
Okay, so the goal in this section is to try to understand why is superfluid helium a superfluid. And the reason that I'm going to explain this in this way is because the explanation is wrong. Okay, so I'm going to show you an argument that Landau made, which I think is a wrong argument, but it's historically interesting. And it's interesting because of the way that it is wrong and why it is wrong. And this is a kind of misconception about superfluidity and superconductivity that persisted even till fairly recently. I mean, I remember when I was first working on high temperature superconductivity, the prejudice amongst other physicists was that superconductivity arose from having an energy gap. And really the reason for that prejudice came from this argument. And so many physicists at the time thought that the high temperature superconductors were S-wave superconductors. And I didn't think that. And it took a long time to convince the community that they were not S-wave superconductors. But part of the reason was for not understanding why things are superfluid and superconducting in the first place. So this is this is an interesting picture, and it's not completely worthless. It does tell you something about phenomenon in a superfluid, just not the phenomenon it was meant to try to explain. So the argument is twofold. What we're going to do is start off by considering the kinematics of superfluidity. So it's a kinematics-based argument. And then when we've gone through the argument, we'll talk about its limitations and so on. So we're going to start off by considering a helium at 0 temperature, and then later we'll do it at higher temperatures. So the way that the argument works is it asks the following question: how can dissipation occur in a fluid and the reason you want to know how dissipation can occur is because that's equivalent to saying, how do you get friction? So that's the question. And so the answer is that if there is going to be friction, then what that means is that some kinetic energy as the fluid flows is converted into thermal energy. And that means that if you heat up helium, that means that you have to make transitions to excited states. So in order for the liquid to heat up, then it must at least go into the lowest excited state, so i.e. at least the lowest excited state, and if you're going to do that, then that means that you must create an elementary excitation. So this is going to be an elementary excitation of the fluid that is moving at velocity v. So this is an elementary excitation of the fluid moving at velocity v. So then the idea of Landau is that we should then consider the kinematics of this process. And you can think of it as being kinematics in just the same way that you probably in your elementary special relativity class worked out the kinematics for particle production in simple system. So the approach is sort of kinematics, somewhat like relativistic particle production. Of course, this is not relativistic and so on, but the whole idea that you can use kinematics to work out energy thresholds is correct. And so when we talk about the kinematics, what that means is that the question that we have to ask is it energetically feasible to create an excitation given the form of the dispersion relation So that's the way we want to try to frame this argument. So the way we consider this is we ask the following. So we transform to the frame which is co-moving with the fluid. And then in this frame, consider an excitation with momentum P and energy epsilon of P. So that's the strategy of this. So now let's work that out in detail. So first of all, we have to work out the transformation of the energy and momentum from the co-moving frame to the lab frame. The lab frame is where we measure stuff. So the momentum in the lab frame is just equal to the momentum in the co-moving frame plus the momentum of the liquid. So let's suppose the liquid has mass m. Mass of the liquid, then the energy, then that's what happens when you do a boost in the lab frame to the momentum, and then the energy in the lab frame is just 1 over 2m p plus mv squared plus the energy of the excitation. And so when you work that out, what you get is p squared over 2m plus p dotted with v plus 1/2 mv squared plus epsilon of p. So that's that's just simple kinematics. So now what we want to know is what is the change in energy due to the creation of the excitation. So we want to calculate the change in energy due to creating the excitation. So we have to imagine that we look at the difference between the energy with an excitation and the energy without an excitation. So that energy we will call delta E lab. And what that is going to be is just epsilon of P plus P dot V. So the terms with capital M are just what you would have if the excitation didn't exist. And so the change due to the excitation is this term here and this term over here. And then of course what I'm going to assume is that the mass of the liquid is going to go to infinity. So we're also going to take the limit that that this mass of liquid m will eventually go to infinity. Okay, so that's the change in energy in the lab frame. Now the kinematics comes in, because you're going to say that this reaction will not occur unless delta E is less than 0. So the transition to the excited state is favorable energetically if delta E is less than 0. So what we want to do then is we want to ask ourselves, what do we have to do to make delta E as negative as possible. And so you can see that delta E has got these two terms here. So this is certainly something that is positive. This thing could potentially be negative. So we want to make the best chance of having this transition occur. We want to make P and V oppositely directed so that we can have the best chance of making delta E negative. So to maximize the favorability of this, I don't know if favorability is a word, but it is now. To maximize the favorability of this transition, we want to make P dot V as negative as possible. And so that means that P and V have opposite directions. And if they have opposite directions, then the dot product, P dotted with V, is just going to be minus P times V, where those without vector symbols are just the magnitudes. So then, if that's true, so if we make that condition, then what we end up with is the criterion that if I want delta E lab to be less than 0, then that can be guaranteed if the velocity is greater than epsilon of P over P. And so that's the condition that I need to satisfy. So you might look at this and you say, okay, so velocity is greater than epsilon of P over P, but epsilon of P over P is in principle a P-dependent quantity. So what value do I use? So basically the answer is this. If you can find some value of P where V is greater than epsilon of P over P, then an excitation at that momentum will appear in the fluid. Okay, so that's clear. So we don't really care about which P it occurs. We just want to know, is there going to be such a thing or not? Because if this condition is satisfied, then we will have a mechanism for dissipation. And if it's not satisfied, then our system will not be able to make any excited states, and we will have a superfluid. So what you then ask for is, since we don't care at what value of P the excitation has, then what we will try to do is try to find the smallest value So basically what we can say then is that V needs to be greater than a quantity which is the minimum over P of epsilon of P over P. And I'll call that value, whatever that minimum is, I'll call that VC. And then if VC is greater than 0, then I will get superfluidity. But only if V is less than this critical value VC. So basically, if V is greater than this critical value, then I will be able to create an excitation. If V is less than VC, I'm unable to create an excitation. And the system stays in its ground state. I.e. superfluid. If V is greater than this critical value that we've just calculated, then we are able to create an excitation. And there is a mechanism for dissipation. So now all we have to do is calculate what is this critical value. So the next thing I'm going to do is I'm going to calculate this critical value. So I'm going to calculate it for helium-2, and you could imagine that you do this calculation and you find that it's 0. Okay, so if it was 0, then that would say that any V that is greater than 0, whose magnitude is greater than 0, would cause an excitation to arise, and then you wouldn't have a superfluid. On the other hand, if VC is some non-zero number, then what that says is that as long as the fluid doesn't flow too fast, I have a fluid that can flow without dissipation. So now let's calculate it. So all we have to do is calculate the minimum of the epsilon over P, and that is something we can do by calculus. So let's do that. So we need to calculate the minimum of epsilon of P over P, and so we can calculate that. That's just d by dP of epsilon over P is equal to 1 over P epsilon prime minus epsilon over P squared, and that thing has to equal 0. And so what that says is that the condition for a minimum is that epsilon at PC, so this is going to be true at some P equals PC, so we want this to be true at P equals PC. And so that says that epsilon of PC over PC is equal to d epsilon by dP evaluated at P equals PC. So that's what you get just from doing the differentiation. So let's see what that means graphically. So here is our curve of epsilon as a function of P. And we saw earlier on that this thing looks something like this, like that. And so what this condition tells you is that the d epsilon by dP is the gradient to this curve, and epsilon over P is just a line that starts here at the origin and is tangential to this curve. So this is the curve. Epsilon over P is equal to some constant. So that's this curve that goes out from the origin like this. And we want this constant to be equal to the gradient of the energy spectrum at the point where it intersects. So here is the point where it intersects over here. And then this value over here is the critical value PC. So you can work that out. You can calculate what that value is, and from that you can then calculate what the critical value is, which is VC. And so when you do that, what you get is that VC is about 60 meters per second. So that's Landau's argument. It's a very clever and ingenious argument based on kinematics, based on figuring out what it is that causes a fluid to lose energy. So it's not correct. And before I tell you why it's not correct, I want to just explain to you how we extend this argument to temperatures that are non-zero. So what I told you up to now was true at 0 temperature. So now let's ask what happens when we extend this argument to t greater than 0. And I'm going to tell you the argument, although I don't actually believe that it's correct either. So the argument goes like this. At non-zero temperatures, there are already pre-existing excitations in the system. And I never really used their existence in the previous argument. We didn't care about pre-existing excitations in our t equals 0 argument. And so the previous argument carries through when t is greater than 0. So in other words, really what the argument is based on is Landau's argument only concerns the kinematics of a new excitation. Okay, so what do the pre-existing excitations do? So Landau would say that the pre-existing excitations they certainly can transfer momentum to the walls. In the usual way. And so that means that the fluid of a pre-existing excitations behaves like a normal fluid with viscosity. In other words, they behave like the normal component of the superfluid. So I think that's fine as far as it goes. The difficulty with this, the slight problem, I would say, is that we use the criterion that delta E should be less than 0 is the criterion to create an excitation. And that just says, that's just energetics. But as you know, when you're talking about thermodynamics and non-zero temperatures, the energy isn't the only thing that matters. You also have to worry about the entropy. And so what really matters is whether you minimize the free energy and not the total energy. So the point is that delta E being less than 0 is a criterion to create an excitation, and that's only true, strictly speaking, at as t equals 0. So you would really need to take into account the entropy as well. So you have to make you'd have to make some modification to this argument. Okay, so that's Landau's argument, and I want to now explain to you whether it's right or whether it's wrong, and whether it agrees with experiment or not. So let's make some comments now. So first thing is that there is indeed a critical velocity. So that's true. However, the VC that you measure in experiment is much, much less than 60 meters per second. So that's there is a critical velocity. That prediction is correct, but it certainly isn't due to for the reasons said. So what do we think is going on? So the problem is that there are other excitations that can be created. Not just quasi-particles. So the one that seems to be the most likely limiting factor is vortex loops. So what people think is happening is that you have a system like this. So here are the walls. Here's the superfluid in between. And then somewhere in the middle of this thing is a vortex loop, like this, a vortex ring, and the fluid is moving like so. And what happens in this particular case is that the quasi-particles can scatter off the normal core of the vortex loop, which transfers momentum between the two fluids, and this is what gives you the critical velocity. So as a way of calculating that, there's an estimate which I'm not going to go through, but which goes something like this. For a vortex ring, of radius r, then the epsilon turns out to be the following. So it goes linearly something like this, and and P is given by rho s pi r squared h over m. And so then if you go ahead and calculate what the critical velocity is, what you get is h bar over rm times the logarithm of r over r naught. And this gives you a number if you plug in the values, which is in reasonable agreement with experiment. So that's probably what's really going on. That if you want to ask what is the critical velocity, it comes from a different type of excitation than the one that Landau's argument assumed. At the time that he did his work, they didn't know yet about quantum vortices. So that's one of the problems of his argument. There's another thing that you may have noticed about his argument, is that Landau's argument doesn't involve quantum mechanics. And it certainly doesn't use the idea of off-diagonal long-range order. So his argument really does apply for something called a Cherenkov radiation, which some of you may have heard of. If I have a particle moving faster than the speed of sound in a fluid, it will have a mechanism for losing energy, and that is exactly this kinematic argument. In fact, this argument is pretty much the same as Cherenkov radiation. And so what that means is that if I take, say, a particle like a neutron and try to fire it through helium-2, it will start to dramatically lose energy. When its velocity is greater than 60 meters per second, because it is literally shedding quasi-particles, and that has been observed. So Landau's argument does tell you about something. It's just not the real reason why you have superfluidity. Now, another thing is, suppose that we ask at ideal bosons. So we already saw that they have off-diagonal long-range order. But does that mean that they are superfluid? So the answer is, well, let's calculate it. So for ideal bosons, the dispersion relation is epsilon goes as p squared over 2m. So now you can plug into my formula, and what you will see is that if I do that, the VC that I get will be equal to 0. So the answer is no. So ideal bosons will not really be like a superfluid. So then you might ask, well, so how does it work with superfluid helium? So what that means is that the following: that when I include interactions between bosons, must somehow give the linear spectrum and the speed of first sound. And we are going to we're going to see that indeed that is correct. That we will calculate the interactions and see how we go from a material that does not have any superfluidity to a material that does. Okay, so that's what I wanted to say about that. Now I want to make another closing point, which is that the real reason for superfluidity is nothing to do with a critical velocity. So so Landau's criterion is a necessary but not sufficient condition for the destruction of superfluidity. So what do I mean by that? So what I mean by that is that there are many examples where there is no energy gap, and yet you still have a superfluid. But just to make sure that you understand what I mean by energy gap, let's go back to this thing here. So remember, this thing is the delta. So this is the thing that we would call the an energy gap. If there is a gap, then you can have this satisfy Landau's criterion. So the examples of these systems are some of the phases of helium-3. So helium-3A has no gap. Another one is D-wave superconductors or P-wave superconductors. So all of these systems are able to have supercurrents in violation of Landau's criterion. Okay, well, so that's all I want to say about this. So what I want to now transition to is a discussion about the temperature dependence of the normal and superfluid densities, and eventually to a calculation of those things, which you'll eventually do in a week or two in one of the next homeworks. So I'm going to move on now to section 3.3, which is the two-fluid model revisited. I'm going to go through this fairly quickly. I want to just go over a couple of simple points in order that you're able to do the next homework. So the goal in this section is to relate the microscopic picture of elementary excitations to the two-fluid model and in particularly the estimation of rho n and rho s as functions of temperature. And we'll be able to do that because if you have a microscopic picture of what rho n and rho s actually are, then we can literally compute that from StatMech. So let's do that, and let's start off by just thinking about superfluidity and the two-fluid model in terms of what we call phenomenology, the symmetries and so on of the system. So what we're going to do now is a kind of phenomenological derivation of the two-fluid model. And we're just going to be thinking about conserved quantities. We're going to be thinking about energy density, we're going to be thinking about momentum density, and we're going to be thinking about what are the ways that these quantities transform under translations and rotations and so on. Try to build a phenomenological picture of what helium should look like. So the basic starting point is that the energy density which I'll call epsilon. I really should call it, this is not the same thing as the energy spectrum. Let me use a kind of curly epsilon. Let's call it like that. This epsilon is equal to some quantity that depends on the superfluid velocity and the normal fluid velocity. And I'm going to write down the momentum density, or if you like, the flux, which I'll call G, and that's going to be a function also of Vs and Vn. So the idea is I have a fluid which has two velocity fields in it. So how do I sort of write down the energetics and the momentum conservation for such a fluid? So the question that we're trying to understand is how do we write down momentum and energy conservation for such a two-fluid system? So that's what we're trying to understand. So what we're going to use are symmetries, which is a theme of this course. So what would we get for normal fluids? So for normal fluids, we know that epsilon is equal to 1/2 rho times the velocity squared, and the momentum current is just given by rho times v. So that's something that you know here. So now we want to ask, well, what happens for a superfluid? So I now have to construct a scalar that depends on two velocities. So that means that I have to write epsilon as some epsilon naught, and then what can I have? Well, I can have a coefficient, which I'm going to call rho s times vs squared, another coefficient, which I'll call rho n times vn squared, some other coefficient, which I'll call kappa times Vn dotted with Vs, and maybe I can think of other things too. And what would those other things be? Well, those would be terms that are of order velocity to the fourth. So this is a low velocity expansion. And every term in here is a scalar, and what I've done is I've chosen the name of this coefficient. So I've called this coefficient rho s and this rho n. In principle, these are some arbitrary coefficients, but will end up being rho s and rho n, as we will see. Okay, so then you have to ask, okay, so what about this coefficient k over here? So this coefficient k has to equal 0, and why is that so? Well, if this weren't true, then the minimum energy of the system say for some fixed Vs would not occur at Vn equals 0. So obviously the minimum energy is going to be the one where Vn is 0, and so therefore that means that I have to have k is equal to 0. So that means that ultimately now we've just convinced ourselves that the form of epsilon has to be some 0 of energy, which I'm not going to bother to write down anymore, some rho s Vs squared plus 1/2 rho n Vn squared plus order Vs and Vn to the fourth powers, something like that. Okay, so that's the energy. So now let's take a look at the momentum of the system. So what we're going to do now is we're going to consider the way we can write down momentum and and of course the symmetry that we're going to be concerned about here is a translational symmetry. So let's work out what happens when we make a Galilean transformation to the system. So what we're going to do with a Galilean boost is we're going to take any velocity, so Vs, and that's going to transform to Vs prime, which is going to be the original velocity plus whatever is the shift that we're making. And the same thing, of course, for Vn. So that's how velocities transform. So how does the energy and the momentum transform? So under this transformation, epsilon transforms to epsilon prime, and this is going to be the following. It's going to be just the original epsilon. Then it's going to be the momentum g dot v, and then 1/2 rho v squared. And how does the momentum density transform? So that's the same thing. And then I've added the term rho v. So once I've got the, once I know what epsilon and g are, then this is how the energy and momentum density transform under a Galilean transformation. So this is just bog standard classical mechanics. Okay, so now the next question that we need to ask, so nothing special here. So the next question is how are G, whatever this is, and rho related to rho n and rho s, these two coefficients that we've written down here. Okay, so and rho is just the mass density of the fluid, the overall mass density. So the way we're going to answer this question is we're now going to is choose a particular kind of boost. So we're going to choose a particular Galilean transformation. So what I'm going to choose is I'm going to shift the boost, the velocity is going to be parallel to the momentum density vector, or the momentum current, like so. So that means then that if I do that, then the epsilon prime by dv evaluated at v is equal to 0. So that's just going to equal g itself, but it's the absolute value of it. And if I look at the derivative of dg prime by dv evaluated at v equals 0, then that is just equal to rho. Okay, just from differentiating these two equations. Okay, so now I can work out what these quantities actually are. So this may seem a little bit strange, but bear with me and you'll see how it all works out. So now I want to ask, so what are these quantities? So the epsilon prime by dv is just, well, epsilon prime just depends on Vn prime and Vs prime. So this is going to be, by the chain rule, the epsilon prime by dVn prime times dVn prime by dv, and these would really be partial derivatives. And then, of course, I have d epsilon prime by dVs prime times dVs prime by dv. So that's just by the chain rule. And now let's go back to our formulas up here on the left and calculate what those terms are. So so the first term here is just 1. This term, the epsilon prime by dVn prime, is what? Good question. Oh, this is just rho n. This is just from here rho n Vn prime. So I use this. So this is rho n Vn, and then this one is 1 times rho s Vs. And so what I've just shown you then is that the momentum G is just rho n Vn plus rho s Vs. So you probably say, well, that's pretty obvious. It just says the total momentum of the two fluid model is the sum of the two momenta anyway. So what's special about that? Well, nothing really, but now we've sort of seen how it comes from just essentially expanding the energy of the system in terms of rho and v. And we can do a similar thing for the momentum dg prime by dv. So that's just going to be dg prime by dvn prime times dvn prime by dv plus dg prime by dvs prime times dvs prime by dv. So that also has to be true. And so you just look back. So these things just from here, this then has to simply be rho n plus rho s, and this is just rho. Oops, I wrote it down as G, but I meant to write road. Okay, so what we've learned then is something which you probably thought was kind of breathtakingly obvious, but isn't as obvious as it may seem, namely that the coefficients of if we expand the velocity in two-fluid model in terms of powers of these two assumed velocities, the coefficients add up to the density and add up to the mass like this. So this is the starting point of the two-fluid model. But it's derived here from symmetry principles. Okay, so now I want to tell you what one can do with this. So what we want to do is we want to calculate. So the question, why is this useful? The answer is we can calculate rho n of t. We can calculate it as a temperature dependence, and that's what you'll do in a future homework. And so the strategy is to compute the total momentum density of the quasi-particles, and then equate that to rho n via. So in the homework, which I haven't given out yet, I will lead you through how to do this calculation. So we're not going to do it in class, but you will do it in the homework. So all I want to do is I want to tell you what the final answer is. So what you're going to find when you do this calculation is that rho n is equal to 2 pi squared over 45 kBt to the fourth over h bar cubed over c1 to the fifth. Okay, so that's the result, and so what I'd like to do in just in the last 4 minutes or so is explain to you what this result means. Okay, so what I want to talk about now is the difference between superfluid density and number of particles in the condensate. So this is an interesting question. So why would you think that they are the same? Well, what you might think is the following. You might think this. That we can define the excited states by calculating the average occupation number of excited states. So let's suppose I've got n particles in the system, and I know how many particles are in the ground state at some temperature T, and then I normalize by the total number of particles. I can call this thing the depletion of the condensate. So this is the average number of particles in the condensate. So what you might guess is the following: that if I compute this fraction of particles that are in the condensate divided by the total number of particles in the system, you might think that this would be the same thing as the number of particles that are in the superfluid divided by the total number of particles in the helium. But you wouldn't say number of particles, you would say superfluid density, that would be rho s, and that would be, and rho would be this. So in other words, you would expect that the depletion of the condensate should equal rho n of T over rho. So that would be a very good guess. Okay, you might think that is, you're just counting how many particles are in the condensate of a superfluid. So what I'm going to show you, we're not going to do the calculation now, but I'm just going to tell you the result, and you'll do it in homework. So the answer to this question, so let's phrase this as a question. So is this true? So this is the question, and the answer is no, it's not true. So and I'll show you why, and then you'll find it hard to believe, but you'll calculate it and you'll see that it's true. So here is temperature, and then what I'm going to plot on the vertical axis is rho n and d of t. So what I already told you was that if you calculate d of rho n, what you get is something that goes as t to the fourth. So this is how rho n of t varies. It goes as t to the fourth. So and you'll see that in the next homework. On the other hand, if you calculate if you calculate d of t, what that looks like is something like this. Oh dear, I'm going to change the color. Sorry about that. Just realized you can't see this. So this looks like so, and this slope here, this is going not as t to the fourth, but as t squared. So this is what you get for an interacting closed system. So it tells you that really this picture of superfluid density and normal fluid density, these are really not to be thought of as number of particles in condensates. They literally are coefficients that go in front of the these terms over here. So these quantities are rho s and rho n are parameters in the the energetics, the energy of the system, and they do not have a simple particle they're not really just counting numbers of particles, as you might naively have thought. And this reflects the fact that these are collective properties of the system. So one last thing, and we'll pick this up next week. So one implication of this is if I write down the energetics, let's just write down rho Vs squared. So that goes as a half rho S Vs squared. Let's just look at that term. So this thing is equal to 1/2 rho S, and we saw that Vs was given by the gradient of the phase of the wave function. So this goes like the gradient of the phase of the wave function squared times h squared over m squared. And so what you can see is happening here is that this coefficient in front of here is the energy cost for phase variations. And so the way we have to think of rho S is that it actually is a stiffness associated with variations in the phase of the macroscopic wave function of this quantum system. So it's not really just counting numbers of particles in the condensate or anything like that. It's an emergent macroscopic property of the system. Okay, so that's where I'm going to end for today's lecture. So let me turn off the recording.